All right, it's time for a little practice. So let's introduce this problem. We have the Building Brick Company, or BBC. They have orders for 80 tons of bricks, and they're going to 3 suburban locations. So Northwood, Westwood, Eastwood, and we have 2 plants, each of which produces 50 tons a week. And the question is, how should we ship the bricks from the plants, these 2 plants, to these 3 locations, knowing that, it costs $42 a ton to ship bricks from plant to Westwood. So that's the setup for the problem, and there's 2 pieces to this. The first one is to draw a network diagram for BBC. So take the words in this problem and parse them out. So how do we illustrate this matrix in a network diagram? How do we illustrate these constraints, $50 a ton and the demand values here, again, in a network diagram? Once we've done that, the next stage is to formulate this as a linear program. So a formal, let Xij equal number of tons of bricks from I to J, blah, blah, blah. So we'll do that. We'll create a network diagram, we'll create the linear program, and then of course the last step, once we have the mathematical model, is to pop the whole thing into Excel and solve it. Right? This is a very mechanical step, and we'll do that one at the end. All right, let's draw a network diagram for the BBC Brick Company, shall we? So BBC Brick Company has 2 plants. We have plant 1 and we have plant 2. And we know that the available capacity at plant 1 is 50 tons and 50 tons at plant number 2. On the other side, on the demand side, we have 3 neighborhoods that we're driving our bricks to. We have Northwood, Eastwood, and Westwood. And just to simplify things, I'm going to just have this as N, E, and W. And we have demand at each of those locations as well. So we have 25 tons over here, and 45, and 10. The matrix tells us that we can get from node 1 to node n. Okay? And every brick that we ship, this will be our decision variable, x, 1, n, has a cost of $24 a ton. So let's put the cost here in blue, shall we? 24. And this is dollars per ton. So if I have dollars per ton multiplied by tons, I'm left with dollars. So to keep things nice and clean, I'm just going to have the costs here in blue, and I'm not going to have my decision variables on my network diagram. Those will come later when we do the formulation. So we can go from 1 to east, and 1 to west, and from 2 to north, 2 to east, and 2 to west. And it's $24 a ton, $30 a ton on that arc, $40 a ton there, and for plant number 2, it's 30, 40, and 42. The only other thing that I would do at this stage would be just to verify the total supply and demand. So let's add up. 50 and 50 is 100 tons of supply. 25 and 45 is 70, and 10 is 80. So my supply exceeds my demand. That's okay. That means I'm going to be able to meet demand, which is good. And I'm going to have some leftover bricks at plant 1 or plant 2 when I'm done. So, network diagram, I have my nodes, I have all of my arcs, I have all of my costs. I've basically taken that matrix and created this wonderful network diagram. What we're going to do in the next stage is we're going to take this and we're going to transform it into a mathematical program, a linear program. The last step will be Excel. Like I said, we're going to formulate this famous diagram here as a linear program. So, same pattern that we've used before. Let x, I, j, our decision variables, equal number of tons shipped from node I to node j. And we can say I equals 1 to 2, j equals 3, 4, 5. Okay, so those are the decision variables. Now we have to write an objective function in those decision variables. So we're given cost, dollars per ton, so we want to minimize total cost. Minimize Z equals, you can use double sigma notation. So sum up everything from I equals 1 to 2, j equals 3 to 5, xij times cost ij, where these are the cost values. So this $24, for example, cost from 1 to 3, that's my $24. And again, this was 3, 4, and 5. Okay, so number of tons times the cost per ton. If you don't like that notation, you can always write it out long form. So I got 24 times x, 1, 3 plus 30 times x, 1, 4 plus 40 times x, 1, 5 plus 30 times x, 2, 3 plus 40 times x, 2, 4 plus 42 times x, 2, 5. And you'll note that the way I wrote that out mimics the matrix that we had up here. Okay, now we have the constraints. So we want to minimize that subject to some constraints. Constraints fall into two flavors. We have our 2 plants. We can't ship more than we have. So we have the amount of product coming out from 1 to 3 plus the amount from 1 to 4 plus the amount from 1 to 5 must be less or equal to the 50 that we have available to us. Likewise, from 2 going into 3, from 2 going into 4, 2 going into 5 is less or equal to the 50 that we have available there. So those are the supply constraints. We have 2 supply nodes, plant 1, plant 2. We have 2 constraints. And on the demand side, we have 1, 2, 3 locations. We're going to have 3 demand constraints. So everything going into 3 comes from 1 to 3, 2 to 3 has to equal the 25 tons. Everything coming into 4 from node 1 or node 2 has to equal the 45 tons that's demanded there. And finally, everything coming into node 5 from 1 or node 5 from 2 has to equal the 10 tons that's required there. So you can think about it this way. We got our table set up, go across this way. Those are the supply constraints. I got 2 of those rows. I got 1, 2, 3 columns, 1, 2, 3 demand constraints. And finally, our old friend non-negativity. So x, I, j is greater than or equal to 0 for all values of I, j, or you could say x, I, j greater than or equal to 0 for I equals 1 to 2, j equals 3, 4, 5, something like that. Just indicate that we're dealing with non-negativity. So we had, whoops, wrong one. We had this famous network diagram. We have this problem formulated as a linear program. The next step is to take this LP, plunk it into Excel, and solve it. All right, what I'm going to do is I'm going to do the building brick company. Or BBC in a quick little Excel spreadsheet. The first thing I'm going to do is I'm going to recreate the cost matrix. So we have our from and our to. We are going from plant number 1 and plant number 2. And then our two locations are Northwood, Eastwood, dad joke, and Westwood. Okay, and then we'll put the values in here. So it's $24 a ton, and 30, 40, 30, 40, $42 per ton. Just put a little label on there so we can kind of keep track of things. So this is the cost matrix. Okay, these are going to be the coefficients for our decision variables in the objective function. And then down here, let's put our decision variables, shall we? Decision variables. Again, what I'm going to do is just copy this, copy that. So these will be the actual decision variables in here. The other things I just pasted in there are labels. There we go. And we'll give them some values, sort of initial values to start, help us build our model. So we're going to add up all of these tons of bricks and so on. And what I'm going to do is create my objective function first of all. Where's a good place to put it? Yeah, let's put it down here. You'll see why in a second. So our objective function is pretty straightforward. We're going to sum product all of these coefficients and all of these decision variables together. And this will give us our cost. Okay, and again, we want to minimize our cost. And this is a very special cell, so it gets all the special treatments. There we go. So if I move 1 ton of bricks from plant 1 to Northwood, I should incur $24 in cost. And I do. Okay, so it's working. Let's do 1 from plant 2 to Northwood, 1 from plant 1 to Eastwood, 1 from plant 1 to Westwood. That should be $100. It is. Okay, so that's working. That's good. Zero that out. That's good. We have the constraints, so we want to add up all of the stuff coming out of plant 1, add up all the stuff coming out of plant 2. So let's do that. Sum. Oops. Okay. Sorry, error message. Yes, I put the bracket backwards. My bad. Okay, let's add up everything coming out of plant 1. Okay, and everything going out of plant 2. That has to be less than or equal to the 50-ton capacity that we had. Okay, just to recap, add everything up. These are calculated values. That's the left-hand side of the constraint. Less than or equal to the right-hand side values. Okay, so these, let's put a title in here. Supply side constraints. Delete that, delete that. Okay, so those are my supply side constraints. On the demand side, what I'm going to do is I'm going to add up everything in this direction. So everything for Northwood from plant 1, everything for Northwood from plant 2, likewise for Eastwood and Westwood. And those are my demand, left-hand sides. Those have to equal my demand at my various locations. So what did we say was demanded? 25, 45, and 10. And we want to have this left-hand side equal to this right-hand side. I'm just going to put a little equal sign in. If I type equals, of course, Excel will give me an error, or it'll be expecting a formula. So I'm going to use a single quote and an equal sign, and then I can get a literal string equals. Okay, so add up all the demand this way, add up all the supply that way, and we have this nice kind of two-dimensional looking problem, right? So we could call these things demand constraints. Whoops. And get rid of that left-hand and right-hand side kind of stuff. And we'll just, make this same kind of thing over here. Supply constraints, demand constraints. It's all good. So let's solve this problem, shall we? Data solver. Solver params. Set objective cell. Cost. We want to minimize our changing cells are all of those. Add a constraint. Add. So we'll do the supply side first. So these two values for our two plants must be less than or equal to the available supply capacity at those locations. And we'll add another constraint. These amounts coming into our three markets must exactly equal the demand at those locations. Okay? Make everything non-negative. It's an LP model. Solve it. There we go. Solver found a solution. All constraints are satisfied. Okay, so let's take a look at what we do. First of all, you can see that shipping from plant 2 to the 3 locations is more expensive, right, for all of those locations. So what we do is we're going to use all of the bricks that we have at plant number 1, all 50 tons. We're going to have 20 tons left over at plant number 2. We're not going to ship them all. We're going to ship as much as we can at low cost. This is the 30 here. And that will meet the demand for Eastwood. The second highest demand is over here at Northwood. So we can ship out as much as we have left over, 45 plus 5 is 50, ship out 5 at $24 a ton, and then ship out the rest of the 25 at 30. And we have no choice but to ship out the 10 from that go into Westwood from plant number 2 at $42. The entire network is optimized. Okay, so this is the lowest cost solution right here, this shipping model. There's our low cost, $2,490. And again, like I said, we got 20 tons of bricks left over at plant number 1. That's the Excel solution. Save my work.